Sound is a longitudinal wave in matter. Remember that sound is a mechanical wave, so despite what you saw in Star Wars, right, there is no sound in space. Spaceships would explode silently, and that'll be one of our demos. A longitudinal wave, if you recall, is a wave where as a wave travels this way, the motion of the medium is back and forth along that direction. It's along. Okay. We can hear about 20 to 20,000 hertz. And what's interesting to me, though, is that the music occurs in like the first 1,000 of those hertz. And so exactly what the rest of that frequency range that we can hear, what that's for, I do have a good demonstration of that. I'm not going to talk about it right now. But it basically boils down to this. Most sound is more than just one frequency. One frequency would be just like this pure sine wave, like the pure tone of a flute. But most sound is more complicated than that, right? We can tell the difference between a flute and a horn, for example. Okay, and I'll show you these harmonics. Obviously, I can't do it right here. The speed of sound at sea level changes with temperature. So as it gets hotter, the air gets less dense and more springy, right? And so the velocity tends to increase. Those things tend to increase the velocity. And it also changes in the different mediums. Right, so in air, it pokes along at a mere 343 meters per second. If you fill your lungs with helium, this is not the safest thing to do. Okay, then you can briefly talk and sound like Donald Duck or something like that. The sound whips along in water much faster than it does in air, and even faster in steel. Right, this is probably a very approximate velocity there. And I do have a story about at my college, they actually had an underwater speaker system in the Leonard Natatorium, which has now been torn down and rebuilt. Believe it or not. Okay. And then we've got some demonstrations here. We can actually get the sound to travel through the bones in our body. And this is kind of a cool thing, but let's not spend any time here with that. So, example, what is the speed of sound at 20 Celsius and 42 degrees Celsius? Well, we just do this, right? So at 20 Celsius, this is sort of an approximate formula, by the way. I'm sure it's not exactly linear, but at 20 Celsius, our velocity is going to be 331 plus 20 times 0.6. Well, 20 times 0.6 is 12, right? So 331 plus 12 is 343. Meters per second, right? So 20 degrees Celsius, when we use 343 meters per second, that's what we're talking about. That's kind of the standard whatever, right? Okay, 42, it's going to be faster, right? So 42 degrees Celsius, our velocity will be 331 plus 42 times 0.6. I think this is higher mathematics. It cannot be done. 331 plus 42 times 0.6. That's 356.2. So just keep this in mind. If you do a speed of sound lab and you're doing it with like a trumpet or something like that, the air inside that trumpet's going to be much warmer than the air temperature in the room. Also, the sound might travel a different speed in the tubing of a trumpet than it does in the openness of the air. But anyway, that's that. There's some examples of these problems you can try. But I think that's it for now.